Hi, this is our video lecture on vector fields. So vector fields are kind of the natural next extension for how we describe space and how we describe the world around us. So we start obviously with just scalars, right, which are just magnitudes. It's our regular numbers, our counting numbers. Then eventually we use vectors, which have magnitude and direction, except we can move those vectors anywhere we'd like in space and make our parallelograms and such. Vector fields are going to give us magnitude, direction, and position. So now we're going to have vectors with magnitude and direction, except they're going to be fixed in a certain position. And so the way we're going to do this is that our vector field is actually going to be a function that takes every point in a region, and we're going to be sticking with 2 dimensions or 3 dimensions for Calc 3, but it could be extended to higher dimensions as needed. But it takes every point in that region and is going to assign each point a vector. And again, there's going to be a function that defines how we do that. So let's take a look at an example here to start off with. So given the vector field f hat of x and y. So again, notice it's very much like our function of 2 variables, except there's obviously the hat on top. That's how we know it's a vector function, right? So it's a vector function for, well, a field. So it's a vector field definition. And what we're going to do is we're going to have an equation that defines how we scale I hat and an equation on how we scale j hat. And typically this is usually the way it's written with individual functions scaling I hat and j hat. But you could of course also write this in the component form as well. So let's just take a quick look at, well, how this actually works in practice. So let's take a few random points in space and see what the vector associated with that point would be and how we would plot that. So let's start with the ordered pair 1, 1. So again, I would write this as f hat of 1, 1. And what I'm going to do is basically plug in that ordered pair for all my variables. So 3x, so 3, well, but I'm replacing the x with the number 1 in the I hat, plus, and then y minus 1, except for replacing y with, well, in this case, 1. So 1 minus 1 in the j hat direction. So we just simplify this a little bit. 3 times 1 is obviously 3. So this vector is going to be 3 in the I hat direction, and then 1 minus 1 is 0, so it'll be 0 in my j hat direction. So what we're going to do now is, on our coordinate plane, find the ordered pair 1, 1. There it is. And from that ordered pair 1, 1, now we're going to plot the vector 3i plus 0j, which really is just, well, 3i. So we go out in the I direction 3 units, and there we go. Now let's try to plot that next one. So the next one is going to be -1, 3. So we plug that into our vector field function. So 3 times, replace the x with -1 in the I hat direction, which is clearly going to be -3 in the I hat direction, plus 3 minus 1. I replace the y with 3 in my j hat direction, which is going to be 2. So with the ordered pair -1, 3, so again, find that ordered pair. So there's my ordered pair -1, 3. From that ordered pair, now we need the vector -3i plus 2j. So -3 in the I hat direction, and 2j, and there we go. That's my next vector. All right, hopefully we're kind of grasping the pattern here. So we'll do the last one a little bit more quickly. So 0, -2. Well, if I plug in a 0, 3 times 0 is, well, 0. So 0 in the I hat component, plus, and if I plug in -2, -2 minus 1, it's going to be -3. So -3 in my j hat component. Again, find the ordered pair, so 0, -2. And then we just put in our -3 j hat vector. And there we go. Now, this vector field is going to be defined for every single point in space, right? Or I guess in my plane here. This is a two-dimensional vector function. But it's going to be defined for every single point here. And I could go through and do all infinity many points and do infinity many vectors, but it's going to look like a gigantic mess. So typically, although we could do this by hand, and that is kind of useful sometimes, typically technology is the way to go. And so when we do look at vector fields, again, they're typically going to pick just enough vectors so you get an idea of what's going on. You can get an overall feel for what the vector field looks like. And a lot of times, too, the technology is going to actually scale the vectors so that the vector field is much easier to read. You could see with that last example that some of those vectors were pretty big, and they're going to start overlapping quite a bit, and we don't want our vectors to overlap. So when I use technology, and I use GeoGebra, which if you just Google GeoGebra vector field grapher, you should be able to find it fairly easily. This is what it looks like. And so that last one that we had plotted, which was the 0, -2, you can kind of see that down here. That is a tiny, tiny little vector, where in reality, it should be a vector that's -3. It should be all the way down there. But, right, that would make it impossible to actually read the vector field. So they do scale it quite a bit with technology so that you just get an overall idea of what's going on. And I'm going to explain what that means in just a minute, and how we can use the vector field graph to actually make some connections. Now, our generalized vector fields, again, there's going to be functions that define the magnitude of each of our, I hat, j hat, and k hat, right? That's standard basis. We typically use p, the function p, in the I hat direction. Whether we are in 2 dimensions or 3 dimensions, the I hat is always going to be p. Q is always for the j hat direction. And then if we are in 3 dimensions, we will need an R function to define k hat as well. Now, you can kind of see that this notation can get really, really bulky very quickly because these are all functions of multiple variables. But hopefully, if we just remember that they're functions of multiple variables, we don't have to write x, y, or x, y, z for every single one of these. And it's going to be much, much easier and neater to just write our vector fields like this, depending on which dimension we are in. And again, those are probably the 2 most typical ways you'll see vector fields written. We will occasionally use the component notation, right? That vector component notation as well. We'll jump in between, back and forth a little bit, because we should be comfortable with both of these if we want to be good at Calculus 3. And I'll try to point it out in the beginning, but of course, as we move on, hopefully we just become more and more kind of comfortable with what's going on and all this hidden notation, which, again, hidden notation isn't anything new in math, right? For example, if I had 6x, we know that's really 6x to the 1, right? We just don't write the invisible 1 because it gets bulky and unwieldy. And it's kind of the same idea here. So just make sure you're comfortable with the notation, you understand what's going on. You should hopefully be fine. Now, one of the most important vector fields is called the gradient vector field. And we've already looked at the gradient quite a bit. I've tried to make a point of making sure that we've seen the gradient quite a bit because it does come up very frequently in this chapter as well. And so our gradient, remember, is that kind of upside down triangle f, where we take each of the partials with respect to x in kind of order. So for example, if I was given the function z equals f of xy, x squared plus y squared, the gradient, well, the partial with respect to x is 2x, because the derivative of x squared is 2x, and y squared would be the constant. And then similarly, the partial with respect to y would be 2y. Now, here is the genius part of all this. Looking at this gradient is actually going to help me understand my original function as well. And let's talk about why that might be. So, before I do that, I want to also bring back another concept from earlier in our course, which is the level curves, which is from the very beginning of chapter 14, when we just started talking about functions of 2 variables, and we talked about our level curves, where, again, it was in the context of height. You know, we have any region that's the same height is kind of connected with that line, and especially we looked at the topographical maps and that sort of stuff as well. But again, level curves, that is the definition, right? You take your function, you set it equal to some constant k, you pick a bunch of various values of k, it doesn't necessarily matter which one, and then you graph them. Now, for this particular example, my function was f being equal to x squared plus y squared, so I'm setting that equal to, again, some constant k, but again, hopefully at this point we know that that's a circle, and so our radius is going to be the square root of k. Right? Because it's always x squared plus y squared equals the radius squared, and just kind of working backwards. So, again, we're going to combine our level curves so that we can see in just the xy plane our level curves, or our traces, right? Those projections, and the gradient. And remember that gradient, back when we did chapter 14, tells us our rate of change, and is going to point in that maximal rate of change as well. And so here's that function in 3 dimensions, paraboloid shape here, x squared plus y squared. And by finding the gradient, right, that 2x comma 2y, and doing my level curves, which I know are the circles, I can plot those together. And if I know how to read this 2-dimensional picture on the right-hand side, it'll help me understand what the original function actually looked like. So, a few things to point out. First of all, every single one of these vectors is pointing out from the origin. And again, if I draw my vectors here, notice as I draw lines out from the origin, it's going to be exactly matching up with the direction of those vectors, right? So all the vectors are pointing basically directly away from the origin. We can also see that close to the origin, I have these very little tiny vectors. So it's pointing away from the origin, but it's very small as we're closer to the origin. But as we get further out, those vectors get bigger, which means, again, the gradient is the rate of change. It means the function is changing more, or it's getting steeper as we get further away from the origin, right? The magnitude is increasing as we leave the origin, which means it's definitely getting steeper. And so that kind of makes sense, right? Here is the origin of my 3-dimensional function over here. And as I move out, right, those gradient vectors, very small. But then as I start getting further and further away from the origin, the slope is becoming greater and greater. That rate of change is increasing. And so my vectors are getting bigger and bigger. Now, that corresponds with the level curves and what the level curves are telling us as well. These level curves, we can see, and again, if you remember, when level curves are far apart, like they are here, right? They're kind of far apart. That means there's a small rate of change. But when they get really close together, like say out here, further away from the origin, when the level curves are really close to each other, that means the rate of change is getting bigger, right? It's definitely steeper. And so we can see with our level curves and with our vector field, our gradient vector field, being graphed together, it's all confirming that same information about our original function and gives us a much better way of trying to understand what that function is without necessarily having to do anything in 3 dimensions, which is a much more difficult frame to usually get your head around or to visualize without more advanced technology. So like I said, right, the magnitudes of the vectors get larger as we move away. That tells me the rate of change is increasing as we move from the origin, meaning the function is getting steeper as we move away from the origin. And of course, that's confirmed by the graph, right? And of course, the level curves also confirm that same idea. Now, one of the most important concepts for this entire unit is the concept of a conservative vector field. Now, if we were to try to work in the opposite direction of what we just did, where I was given a function, right? Previously, I was given a function and I found the gradient field associated with that function. Now I want to know, if I was given a vector field, could I work backwards and show that it is the gradient vector field of some function? Can I work backwards? So again, if I'm given some vector field, right, f of x, y, can I show that this is going to be equal to the gradient? Is this vector field going to be equal to the gradient of some function little f? And again, that means f partial x, comma, f partial y, right? Can I make those match up? Does p equal my f of x? Does q equal my f partial y? Now, to see if this is true, we want to take the indefinite integral of p with respect to x, again, working backwards, the indefinite integral of q with respect to y, again, trying to work backwards, and then seeing if we can build what's called a potential function from those two results. Now, a good place to start, too, is actually with Clairaut's theorem, because if a potential function is possible, that means that Clairaut's theorem must hold as long as, that function is continuous. And so what I mean by that is, for example, we want to check if p partial y equals q partial x. Well, p partial y, remember, we're trying to show that p is really f partial x. So then it's f partial x with respect to y, so f xy. Q of x, q partial x I should say, is again asking, well, q is supposed to be f partial y, and if I take that derivative now with respect to x, I get f of, yx, and by Clairaut's theorem, those should be the same if my function is, continuous. So again, that's what we're going to try to show. So let's try to work through our first example, right? And let's see if I can get backwards, actually, right? Can I show that this was my original potential function if I was only given my vector field? So given my vector field like this, if it was the gradient, that would mean that f with respect to x, right, f partial x, I should say, was 2x, which means what I want to do is, again, work backwards. Integrate now with respect to x. So integrate 2x dx. And so the antiderivative of 2x is obviously going to be x squared. And it's an indefinite integral, so it's plus c. Except, wait, it's not actually plus c because we're talking about functions of multiple variables. So instead of plus c, again, this is going to be a function of that other variable. In this case, a function of the variable y. And again, typically we use g of y to represent that. Now we work with the other part, f partial y, assuming that, again, that is the partial. So that was 2y. And very similarly, integrate now 2y with respect to y, which gives me y squared plus c. Except, wait a minute, we just said it's not plus c, right? In this case, it's going to be a function of my other variable. So it's going to be the function of x, or in this case, h of x. Now, to find a potential function, we need to match these up. We need to see if I can build a function from these two results. If I take these two results together, can I build my function? So I know my function f. Well, it needs an x squared from my first. And then it might have some function of y. Well, that function of y is going to be the y squared from my other equation. So plus y squared. All right, and I look at my other answer, y squared plus h of x, except I have the y squared already, right? That's taken care of, check. And the h of x, a function of x, well, yeah, that was my x squared from earlier. So yeah, that takes care of it. And sure enough, I was able to build my potential function as being x squared plus y squared. Now, this is typically how I do it. I take my two antiderivatives and I just try to match it up. I try to build my function from the results. I basically know what it has to contain, what overlaps, and it makes a lot of sense to me that way. It's the same way that I would find, the common denominator of a fraction, right? If I factored. That same type of idea of trying to match up denominators. But your book does a more detailed kind of algorithmic approach to how to actually find these by taking the antiderivatives and then taking the derivatives again. And that certainly works. And it's a great method. I find it to be a little bit longer. And, if what I just explained didn't make a bunch of sense, read the book. Again, their approach is pretty straightforward, and it's one that's going to work every single time as well. I just don't find it to necessarily be worth the time. But oh well. Now, here's why that is an important question. If I'm given a vector field and I can find the potential function, it's not always going to be possible, but if I can find that potential function, that field is going to be conservative. If a potential function exists, my field is conservative, or we call it a conservative vector field. And that is critically important. Well, you're going to see when we get to section 16.3. So let's take an example. Given a vector field, can I work backwards and find a potential function for it? So, let's see. Again, I'm going to kind of isolate here. Here's my P. Here's my Q. Those are my two functions. P would be, again, my partial with respect to x. Q would be my partial with respect to y. So in this case, P is negative 2y, and Q is the function to x. To check to see if a potential function could exist, before I even start taking antiderivatives, usually it's a good idea to try to use Clairaut's first, right? See if we can't, see if it's even possible to find a potential function before we start taking antiderivatives, because typically the derivatives are going to be a little bit easier. Which means I want to find what is P partial y, right? So that I can actually find what's F partial xy. Well, if I take the derivative here with respect to y, what's the derivative of negative 2y with respect to y? Negative 2. All right. Now we have to check that if I take the partial of q with respect to x, which in this case would be f partial y, and then we're taking it with respect to x, so f partial yx. If I take the derivative of 2x with respect to x, I get 2. Are these the same? No, these are not the same. And since they are not the same, there is no potential function. There's no potential function. And we also know that if there's no potential function, even more importantly, we know that this is not going to be conservative. Not conservative. All right. Next example. Given my vector field here. So again, my P and my Q. So again, I would suggest check Clairaut's theorem first. And again, I'm just going to do this very quickly now, if you just did that previous example. So P partial y. Well, what's the derivative of sine with respect to, what's the derivative of sine of y with respect to y? Cosine of y. Then I want to check what's the derivative of q with respect to x. So q partial x. Well, this is x cosine y. So with respect to x, right, cosine y is my constant. Cosine y would, again, typically be factored outside. And the derivative of x with respect to x is just 1. So, yeah, it turns out they do match, which means a potential function should exist, and I should be able to find it. So we're going to go through and just take our antiderivatives again. So when we take that antiderivative of p, Now we take the antiderivative of p with respect to x. And again, this is where it gets a little bit complicated at first, at least when you're first doing this stuff, because you're taking the derivative of p with respect to y, but you're taking the integral of p with respect to x. And we kind of, we change the variables because of, well, I guess, like how it's all defined. And again, that can be a little confusing at first. You can definitely make some mistakes there at first. So take your time, be diligent, write it all out, and put enough care into your work that hopefully you don't make those mistakes. But if I'm taking the integral of p with respect to x, well, p was sine of y, which I could actually factor that sine of y outside my limits of integration because, again, I'm integrating with respect to x, which means my antiderivative is going to be sine of y times, well, x, right? The integral of 1 dx is just x. So I get x sine of y plus, and again, there could be my constant, but my constant is now a function of y, so g of y. Now, integrate q with respect to y. Now, q was x cosine y, which means now I can factor the x outside my limit of integration. So it's the integral of cosine of y dy. And so again, I have that x I factored out, but the antiderivative of cosine of y with respect to y is sine of y. Sine of y. Again, we don't want to forget that there could be that constant, that plus c, which is really a function of x now, so h of x on the outside. And I want to see if I can match it up, except this actually matches up perfectly, right? They share the exact same thing. I don't even need to worry about this other part. And so my function f, my potential function f, is x sine of y. Also, I know that my original vector field up here is conservative, which is very, very important. All right. So hopefully you tried those on your own. Maybe even pause the video and work through it, or do those examples again to see if they made sense. I did include the answers, of course, in your notes, so you can check them as well. But I wanted to finish up this video by talking about our graphs of vector fields and what it means if they are conservative. So this first vector field, again, that was my first example that we showed was not conservative, and it looked like this. This is a graph of my second vector field, which we know was conservative. And now what can we say about these two fields by just looking at them, at just looking at these vector fields? Well, typically what we want to think about is what are called kind of flow lines. And we're not really going to get into flow lines in this course. They are a part of differential equations, actually kind of a big part of differential equations later on. But what a flow line is basically if I were to drop a particle, let's say I drop a particle here in my not conservative vector field, what's going to happen to it? Well, think of this vector field as almost forces acting on this particle. So it's going to move in the direction of that, that vector. And then once it's here, it's going to move in the direction of the next vector, and 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 the next vector. And we keep moving all the way around. And it looks like it's going to, loop back on itself. And that's actually a key feature of should loop back on themselves. If it's not conservative. If I did have a conservative vector field and I dropped a particle in, let's say I drop a particle here, I follow the vectors, and looks like, okay, it's just going off the page there. If I drop in a particle over here, looks like, all right, it's going off this direction. Is it going to loop back on itself? No. No, my conservative vector field is not going to loop back on itself. Again, I just talked about what a conservative and a non-conservative vector field might look like and what might eventually happen to a particle in these fields. But again, important questions to kind of ponder as you go over this. Again, if you have any questions, please send me an email. And hopefully this was informative. Goodbye, everybody.